ASM, Are You Serious? Which I didn't come up with. Joe made up that name. He said he asked me if I wanted to do a talk, and I was like, yeah, and I started coming with all these ideas, and I was like, actually, I think, I was doing some assembly problems. I'll do a talk on assembly. And as I was working on this talk, I realized, yeah, I could do it on assembly, but a talk on assembly is really hard to motivate. You probably don't work in use assembly, and if you are writing, for example, like x86 assembly, there's probably nothing I can teach you about it that you don't already know. So I thought, well, I could do a talk about the machine, like just like the broader concept of computing, and like let's try to build a mental model of how the machine works. That's better, but still kind of hard to motivate. So I realized that, really this is just a talk about having fun. So I wanted to talk briefly about, what was my motivation to learn some of the concepts that we'll go through today. And the reality is I just kind of like learning this stuff. So quickly, my background. So I don't have a college degree, so I don't have like sort of a romantic memory of like writing my own shell in like a computer science course. I started programming as an adult, so there was nothing I hit in my teenage years besides horribly failing to install Arch Linux on a laptop, where I can look back on and be like, oh, I hit that really interesting problem that has some underlying computer science or conceptual thing to understand. I've been pretty career focused for the last 4 years. The 3 years before that, I was at a startup just trying to keep my head above water. Before that, I was busy dropping out of college. So I realized that I just need to, find a way to have more fun with computers. And one of the things I did is I went on a week-long retreat. So I called it like my John Carmack style retreat. So if you haven't never heard of John Carmack, he's a programmer. I've heard he's a pretty good one. But he is known for taking these week-long retreats where he'll actually get in a plane, fly to another state, check into a hotel outside of the airport, lock himself in the room, and learn a new concept. I think publicly he said like one of the recent things he did was he just locked himself in a hotel room with like a laptop with I think OpenBSD on it and forced himself to use just Vim, GCC, and GDB to do development. He called it his Civil War reenactment. I thought that was pretty good, and so I wanted to recreate the own thing. So what I did was, I was like, well, I live in Lexington. I have friends in Bowling Green. I have friends in Louisville. I don't know anyone in Cincinnati, so I guess I'll drive up to Cincinnati, check into a hotel, and study something. So that's what I did. That's my setup in the hotel. With like my Mac Studio and monitors and everything like that. I was fortunate that at the time there was a platform for learning some computer science problems through like working on some exercises that had just gone into a beta. So I was like, well, great, I'll use this as my curriculum. So I went and did like, learned some x86 assembly, did like some C programming, learning how to make like dynamic arrays or hash maps from scratch and some things like that. One of the more fun moments, remember this is a vacation, so I could stay up as late as I want. So I was staying up till about 3 in the morning trying to figure out how to write this DNS client that would actually query an A record from a DNS server in Python without using any libraries or anything like that, just using its thin socket interface. And so I'm there, it's 2 in the morning, too much caffeine for sure, probably too much pizza. Staring at like the hex on the Wireshark UI, being like, I think, like my eyes are glazing over trying to read the DNS RFC. It was a blast. And there was nothing like the thrill of, at 3 in the morning actually being able to query for google.com and get back a set of IP addresses. So all of that's just to kind of show you, like, I just think this stuff is fun, and I'm trying to carve out more time in my life to like just have fun with computers. So one of the things that we're going to talk about is like, let's try to build like a mental model of how like a machines. So to have a machine like a processor or like a, you know, if you think about like your language runtime is like, it's, you know, people call it a virtual machine. You know, what are these like machines? So to have a machine that's useful, we need something that'll fetch data, right? Operate on that data and store the results back. So generally you need a place to store that data quickly. And usually storing that data quickly is cost prohibitive, so you need somewhere to store the overflow of that data, right? So, and ideally we want our, you know, the program that we write, it runs on our machine, we can run it multiple times. So to program the machine, to become the machine, so generally you'll need something like registers, right? In a processor you're gonna have registers, which we can just think of for our purposes as a place to store numbers quickly. We can think of just as a single register as a place to store a single number. And then we need memory, a place that overflow, right? Because something small like registers is going to be cost prohibitive. Then we need a way to program our machine code, a way to tell it what to do. And then we need to have a way that, like a model of where like our machine is going to execute that code. So our machine code is just a bunch of bytes. We'll have our registers, our memory, our machine code, and our way to execute machine code. So our machine, what it's going to do is it's going to fetch a byte, decode it, and do some sort of execution, right? This is commonly referred to as the fetch, decode, execute loop. It's imperfect, but useful mental model for how machines work. So let's start by looking at a problem that's worth solving. And I will say that I totally forgot to set my Apple Watch, so somebody's going to need to tell me when I run over. So let's look at the problem sum to n. So the definition of the problem sum to n is given an integer n, return the sum of the number 1 to n inclusive. So if you have the number 3, right, your result is 1 plus 2 plus 3. So your result of your function would be 6, right? So here's an implementation in Python, right? If you take a moment to look at it, hopefully you can convince yourself it is correct, right? We have the number I. We have the variable I initialized to 0, right, which is our iterator. We have s, which we're going to be accumulating our value through, and then we're going to loop through that and get to our result. If you don't like Python, here's the same implementation in C. Hopefully you can convince yourself that they both have the same result, right? So we have our for loop, and it does, you get it. So but we have a machine, right? It's not we don't have we don't have any of that stuff. So like, what is our machine going to do if all we have is some places to do fast storage and some places to do slower storage, right? So let's imagine we have this machine where we're going to have 2 registers. For our purposes, we can just think of them as just storing a number each, right? So R1 can store a number, R2 can store a number, and then we'll have memory, which we can just think of as an array of numbers or as an array of bytes, where the first 4 positions in our array are where we can store values. So you could think of it as like the RAM on your computer. And the rest of the bytes are actually going to be our machine code. But how do we get to our implementation of sum to n? Right? If our machine, what it's going to do is read a byte at a time in this fetch, decode, execute loop, and it's going to perform operations accessing registers and memory. What else do we need? We need some way to program the machine that makes sense. So first, we're going to represent our registers. How we'll represent them as bytes is we can have them as register 1 is a 1 and register 2 is a 2. To keep it easier to read, I'm going to use hexadecimal notation in a few places. And just as a quick review, if all of the bits are on in a byte, which is 8 bits, you'd have a hexadecimal of FF, and so on and so forth. Hopefully that's clear. So we need instructions for our machine so we can tell it what to do, So we'll have the instructions set, load, store, add, increment, and halt. So set will map to the value 0, and that's to set a number into a register. So if we do set R1, 1, that would set the number 1 into the register 1. Load is for loading a value from memory into our register, and store to store it from a register into memory. Add will add two registers like R1 and R2 together, and increment will increment the value by 1. Halt stops our program so it doesn't run forever. But how do we get the loop with that? So here's a quick representation of a program. Remember, we reserved the first 4 spots for memory, and the rest of the values in our array is our byte code. So if we were to decode these 3 bytes here, we'd see that these would set R1 to 10, right? What we need is some way, right? In our for loop, we check a condition. If that condition is true, we execute a block of code, and then we check the condition again, right? Iterating I as we go. We need some way to, given a position in our code, go back to a previous position based on a condition. We need what's called a program counter, which is, for our purposes, going to be a special register that points to the specific spot in our byte code where we're going to do the next execution of our fetch, decode, execute cycle. So to get us to loops, we have to introduce not just that new register, but a few new instructions. That'll be compare, which will compare 2 registers together and set a flag if it's less than, equal to, or greater than. For our purposes, to solve this problem, we just need less than. So, and then we need a jump instruction that can check that flag and then update our program counter to move us in our byte array. So the flags are conditional values that can get set and cleared during execution. And the labels, which we'll introduce in a moment, are just a convenient way for us to label in our language we've created here what position that we want to jump to. So if we look at just a simple implementation of how could we take our 2 registers, we'll take R1 and increment it until it gets to register R2. So we'll set 11 into R2. We'll have a label of where we want to start our loop. We're going to increment by R1, compare R1 to R2, and then if R1 is less than R2, we'll jump back up to the front of our loop, and we'll continue to do this until we halt. So if we look at our memory with that program now in machine code, now in byte code, our program counter is going to start at 4 because we're offset from where our initial slots in memory are. And our first instruction is to set R2 to 11. So we set R2 to 11. We increment R1. And then we compare R1 to R2. It is less, so we set our less flag. We get to our jump instruction. And the less flag is set, so we jump to .loop, which now in our byte code you see is represented by 7, which is giving us the value to update our program counter to, clearing the flag, updating our program counter, and going back to the start of our loop. And we're going to do it all the way to yeah, I wasn't going to make all those slides. So jumping ahead, hopefully I can convince you that this is in fact correct loop. R1 and R2 are 11. Now when we do our compare, the flag's not going to get set. It's going to be effectively a no-op. And jump is not going to jump because the flag is already cleared. We reach halt and our program ends. It loops. If you thought debugging code was hard, try debugging a slideshow. There's nothing like getting through that set of slides and realizing you have an off by one error. Okay, so what are we trying to do again? Right. We're trying to solve this sum to n problem. Okay, so we already talked through, 3 would be 6 because you would add 1 plus 2 plus 3 to get 6 in our sum to n problem. If you like math and you're like, well, John, there's a constant solution to that, be quiet. You already know too much. So let's see. Let's try to do a solution to this. So like if we set R2 to n and R1 is our counter and we're going to loop it, we're going to okay, let's start over. So we'll set R2 to 3 as our value to n. We'll store that into our memory address 0, and then we're going to enter our loop. And now we're going to set up our counter and accumulator. So one of the problems that we have with dealing with our limited amount of fast storage is that we only have 2 registers that we can use. Our program counter is used to keep track of where we're at in our bytecode. So the only thing we can really modify are 2 registers. But in our problem, we actually have 3 variables that we need to keep track of. We need to keep track of n, how far we're adding up to, s, the accumulation of our values, and I, our incrementer for where we're at, adding our way up to n. So we have to kind of think in our minds and map what spots in memory we're going to hold which values, and then constantly be storing and loading values in and out of our registers to come up with our solution. So we'll say that memory address 1 is where we'll store our counter I, and memory address 2 is where we'll store our counter S. And so in our solution, we'll load both of those into R2 and R1. And then we're going to perform our increment on I. We're going to increment register 2. Then we're going to add register 1 and register 2 together. So when we do an add, it's going to add the values together, and then the result is going to be stored in register 1, just like our expression s equals s plus I. Now we have to check our loop condition. Again, right, we only have 2 registers, so we have to store these values away when we need to look at other values. And so in the beginning we stored n, and now we need it back to check our condition. So we're going to store the value that's in R1 into memory address 2, and then we're going to load the value in memory address 0 into R1. We're going to check our condition. We're going to store I back into memory address 1. Then we need to check our loop to see if we need to loop back through. And then finally, at the end of our program, we'll just say for what we're trying to do here that we want our result in register 1. And then we're going to end our program. Cool. So if we walk through this execution, right, we start at program counter at 4, right? Our memories here on the screen in these 4 slots here. And we have our less than flag. So we'll set R2 to 3. We're going to store that value in the memory address 0. We're going to load the value at memory address 1 into R2, load the value of memory address 2 into R1, increment R2, add them together, store them back, load address 0 into R1, because now we need to check the condition of our loop. We do our compare, it sets our flag, we need to store that value back, right, and then jump is going to set our program counter to 10 and clear our flag. Hopefully I can convince you that this is correct. And if you're saying, actually, you did this inefficiently and you could do this with less instructions, I did this in a weekend. And if you really do think that this can be done with less instructions, please come see me and show me. So we're going through and, hey, Now we have our resulting value, right? We've stored it back into memory. We're about to check our condition. And we're there, right? 3, n, I is less than or equal to n, I is, yeah. Cool. And then we'll load our result into R1. It worked. Let's go through it again. There's a lot of debugging on those slides too. A lot of debugging. So how does it work? So we'll just go through this pretty quickly. But this was a program that I wrote in Python where we kept like a mapping of instructions to just integers of what they are. So like, just like we kind of showed, right, R1 maps to 1, R2 is 2, set 0, like all the instructions up to halt, which we just set as flipping all the bits. I have a way of like interpreting labels. We're keeping positions of where in the file the label is, and then this is like a helper function just to get the actual values written out as bytes. We're not going to go too much in depth of the code, but hopefully you can see, right? It's a Python program. It reads a file that's written in that language that we just constructed here, and does some checks to make sure it's formatted correctly, and then all it's doing is it's saying, hey, if it's this instruction, check these things, and then write those values to give us that structure where it's like the byte of the instruction, and then the registers, and then the variables. And then there's another program that can actually do the execution. So that's actually reading the bytecode. It itself has a representation of the program counter and R1 and R2 and the instructions. It keeps track of a less flag, which is how we're able to do our comparison and jumping. I just wanted to show this here. I do have a show function that I call a lot in this so that I could debug it and step through it step by step. I ended up using it to debug my slideshow because I started executing something and I was like, oh, my slides are completely wrong. And so in the execution, right, if we know what the instruction is, then we know how to interpret the next set of bits. So that's what all of these examples are doing, right? Given a certain instruction, we do different things, right? If we're doing a compare, we know that, okay, well, our next two basically parameters are going to be a register, so we want to pull those and check the values of them and then set our flags and so on. So you might be thinking, well, that's a really nice toy. That's cute. I think I'll stick to C or Python. So if we get back to our original solution, I just want to quickly show you that like what we've created here is actually, it's kind of similar to what you would expect to see in like something like Python. So if you were to take that Python example and you were to use the module dis, which will disassemble it into the instructions that the Python VM calls, what you're going to see is that it actually looks pretty similar. So just to annotate this really quickly, these are the line source numbers. This is the index of the instruction in the Python VM. This is the actual instruction name. And then these are just hints kind of vaguely saying what they are. So you can kind of see like, you see I and S there and N showing what variables it relates to. But if we were to look at this, it's pretty similar to like what we just constructed. We're loading and storing values. Right, we're doing comparisons, and based on those comparisons, we're doing jumps between positions of the code. One difference here is that in our case, we went through the line of execution before doing a comparison and jump. In Python's case here, what it's doing is it's doing the comparison, and then it jumps forward, skipping a huge chunk of code. So you can see, like, you get down to jump absolute, it jumps back up to do its comparison, and if we're at the end of our loop, it's going to jump to our return value. If you were to look at the Python bytecode for this, it's all just bytes, not exactly like our example toy program, but it works kind of similar in the sense that it's, you're pulling these bytes, you're determining what they mean, and you're doing executions on them. If we were to take our C code, compile it, and disassemble it, and actually see the assembly, which despite this talk originally going to be about x86 assembly, I'm not going to explain any of this to you. But we can see that the move instruction in x86 assembly essentially serves the same purpose as our set, load, and store instructions in our toy example. So we can see here in the program, right, we're loading and storing things from memory and into the registers. We're doing a comparison, and based on that comparison, we're going to do a jump if it's greater than, right? So again, this assembly, like that Python example, it's going to jump forward and skip a bunch of code. And if it's at its terminal point versus our example where we went all the way down the execution and then jumped back up. So in the regular case, right, this is sort of the entry of that for loop where we're adding 1, and then you jump back up, right? And then when you're at the end of your loop, you jump down. And we're not going to talk about x86 calling conventions or anything like that, but that's what some of those, the popping and pushing there, we're not going to talk about the stack. I don't have time. Also, I didn't review it. And this is the actual machine code. So if we compile this down and actually look at the file, it's all just bytes. This is just a section of it. It's much bigger than this. But hopefully I've convinced you that there's a lot of similarities between the toy that we've made, x86 assembly, and even the Python runtime. There's everything all stacked against each other. I'm running out of steam. Yeah, so machines are fun. So I'm going to put some of the code examples in the Bluegrass developer Slack in the channel Saturday CS, where I've been trying to share some of these things that I've been learning about and exploring. So take a look at that bookmark, and that's my talk.